Before we get into answers, let's think about key elements of what's under the hood. So I'll go to my usual framework of what's inside the black box. The physical problem is solidification, but the black box or answers is solving a mathematical model of that physical problem. So we'll take a look at what that mathematical model is, the governing equations with boundary conditions and initial conditions. And then the finite element solver will get an approximate solution, numerical solution of that mathematical model and calculate temperature at selected points and at selected times. And then everything else, the color pictures and so on, that we will generate are created from these temperature values at selected points at selected times, and that's a process of post-processing. Let's start by looking at the mathematical model, and in fact the mathematical model for the sand mold. It's a 2D initial boundary value problem, so-called initial boundary value problem for the sand mold. The governing equation is the classic transient 2D conduction equation, heat equation. So on the left side we have the effect of conduction, and this is all applied to an infinitesimal element, in this case within the sand, and this is the change in energy with time, or internal energy. And we need to solve this governing equation and calculate temperature as a function of x and y and time. The boundary conditions, we specify either the temperature or the gradient of temperature, the normal gradient of temperature. At the left boundary, the temperature is specified. At the top and bottom boundaries, it's insulated. Essentially, insulated reduces to that, which means that the normal gradient of temperature at those boundaries is 0. And then this is an internal boundary, and let's not worry about that and let the solver take care of it. The 2D initial boundary value problem for the aluminum casting is a little bit different. You again go to the governing equation for transient 2D conduction, except that now on the right hand side you write the change in energy in terms of change in enthalpy with time. And that's because the change in temperature with time, when there's phase change, is for a pure aluminum is 0, but there's a change in enthalpy. So if I had it in terms of temperature, this term would be 0, but really there's a change in energy, and the change in enthalpy accounts for that. And then we need to give the relationship between the enthalpy and temperature as we saw before. And then the boundary conditions, for the casting are going to be essentially insulated at these 3 boundaries, and this is an internal boundary. And the initial, so essentially the gradient of temperature at those boundaries is 0, and then the initial temperature is 700 Celsius. So that gives you an idea of the mathematical model. And so that gives us an idea of the mathematical model. Next, let's take a look at some of the big ideas in the numerical solution. And this is classic stuff from the finite element method. You divide the domain into elements and nodes. You reduce the problem to determining temperature values only at the nodes. So for instance, this could be a node, this could be a node, this could be a node. So the temperatures would be calculated at discrete points rather than everywhere. And then you would use polynomial interpolation to relate the temperature within an element to the nodal temperatures. So for instance, if I wanted the temperature here, I would just interpolate this, and these 4 values. Very classic stuff. And so we've reduced the problem to determining the temperatures at the nodes at different times. and the solver will generate a system of algebraic equations in the nodal temperatures at each time, and it's going to step through time. And that the system of algebraic equations is going to be generated from the, the mathematical model that we just saw using the polynomial interpolation. So this is, the heart of the finite element method, and then it'll invert the system of algebraic equations to get the nodal temperatures at different times, and everything else is post-processing. Now, an additional complication here is when you write the equation in terms of enthalpy, the equation is nonlinear, so you have to solve it. You have to solve the system of algebraic equations iteratively, and I will get to that when we are in ANSYS. So that brings me to the end of pre-analysis.